Hello and welcome to lecture 31 of Math 2R03. In today's lecture, we're going to start a new chapter. We're going to be looking at chapter 7. And what we're going to be doing in chapter 7 here is to look at special operators on inner product spaces. So in the last chapter, we introduced inner product spaces and we learned some of their properties. And now what we want to do is look at operators on these spaces. So remember, an operator is just any linear linear map from that vector space to itself. So we have now vector spaces that have inner products, and now we're looking at linear operators on those spaces, and then we're going to actually put more conditions on those operators. And the first one that we're going to look at is what's called the adjoint operator. So that's what kind of the very first part of today's lecture is going to be about, is what is the adjoint. Okay, so let me quickly, or not quickly, but go over the definition of the adjoint. So let T be some linear map from a vector space V to W, and the adjoint of T is the function that goes from W to V, so it's kind of going backwards. And so we call that T star, such that for any V in V and any W in W, we have that the inner product of TV with W is the same thing as V with T star W. Okay, so this definition, there's a lot to kind of unpack. And so I actually want to spend some time explaining what exactly this definition is, because the adjoint is saying, okay, it's a function going from W to V, and it takes a W and it maps it to T star W with this particular property. So let's try to spend a couple minutes to understand what's going on here. Okay, so the first thing you have to notice is on the left-hand side, where is this inner product taking place? This is taking place in W. So this is the inner product of W. Okay, and on this side, on the right-hand side, this is the inner product of V. So we have these two inner products, but you got to remember the left-hand side is you're thinking of the inner product in W, and on the right-hand side you're looking at vectors inside of V, and you're thinking of the inner product inside of that vector space. And what it's saying here is that these numbers, right, because remember these are going to be elements of your field, are always going to be the same. That's what the adjoint is doing. Okay, so let's unpack it a little. There's more though to unpack in this definition. Okay, now for any fixed, if we fix a vector W in our vector space W, we can define a map phi from V to F defined by taking that vector V and we can send it to TVW, okay? And this is a linear function. It's a linear functional. So phi, right, once we fix a W, this map here, which takes a vector V, maps it over to W, and then applies the inner product where W is this fixed element, is in the second spot. This gives us a linear functional. Okay, so now this is a linear functional, and this is this is inside of, this element here is inside of W, right? This element here, well, it's also inside of F, but we're using the inner product in W. But now, by the Riesz representation theorem, we know that there's a vector U, because this is a linear functional, there's a vector U such that VU is equal to phi of V, which is defined to be this function TVW. Okay, so the Riesz representation says there's some vector U, and so how does this map T star work, right? So T star, let's go back to here, T star associates to each vector in W a vector in V, and which vector does it associate to? We define T star W to be this U given by the Riesz representation theorem. Okay, so i.e. T star W is the unique vector so that we have that v t star w holds. Okay, now you may want to reread this over and over again and look in the textbook, right? And the point is that this is probably the most complicated definition in the book. At least that's what I think is true. So it's probably the most complicated definition in the book because, right, the map is defined by taking some vector w and mapping it to v, and we're saying that it mapped it to the vector that makes this equality true, okay, for the inner products of these two things to work. Okay. Now, there's something I forgot to mention at the beginning here, and this will kind of help us when we go forward. Okay, so chapter 7 looks at special operators, and the point is that this material, that what we're going to talk about, generalizes results on symmetric and orthogonal matrices that you may have seen if you took Math 2L A3. Okay, if you didn't take that course, that's fine. You could pull out your first year linear algebra book. There'll be a chapter on symmetric and orthogonal matrices, and that's what we're trying to generalize. Okay, and as we go through today's lecture, I'll give you a different way to think about the adjoint of the matrix. Okay, so this is probably the most complicated definition. When we come back, let me just give you I will give you an example and some of the properties of the adjoint.